Welcome viewers. In my lectures today I will discuss about one dimensional unconstrained optimizations. As this name suggests that the input parameters is one dimensional and the parameters is unconstrained. In my previous lecture I have discussed about what are optimization, what are the basic application of optimizations. I talked about constraint and unconstrained optimization. Later on we will discuss about constraint optimization, but in this lecture we will discuss about unconstrained optimization. That means there is no constraint about the input parameters and it is one dimensional. That means what is this? It is basically it consists of the function consists of one parameters. So, what are the basic objectives of optimization? Let me reiterate once again. Determination of the minimum and its location of a real valued function of one variable plays a important role in nonlinear optimizations. Again, nonlinear optimization, that means input function may be linear or nonlinear also. A minimum one dimensional routine may be called several times in a multivariable functions. To that means I can convert this one dimensional function into multivariable function. I can use this rather, and mathematical formulation of this seems like this: determine the x star that minimizes or maximizes the function f x, and mathematically I can set that this one is f x star must be equal to less than equal to f x for all x real valued x. What is this? That means the goal is efficient and accurate estimation of x. Let me give you a mathematical examples so that it can be cleared. Say for this one is this is another classification: single variable or multivariable, constraint or unconstrained functions, analytical method or numerical methods for optimizations. So, in this lectures, this one f x is equal to, let us take a very simple function, f x is equal to this one, x square plus 3x plus 5. So, what is this? By visual observation of these functions, I can tell that this function is continuous and differentiable. The minimum value can be found analytically or numerically. So, as this is a quadratic function, so I can tell that it is a smooth parabola with the unique minimum value. So, like this, so it is why it is one dimensional? It is because the single variable and multivariable function. That means if I put the function in one dimension, one direction, say for f x, then and this one is x, that means this is a single variable. In that such case it is called one dimensional optimization problem. If my function is something like that, if my function is with respect to this, if my function is x1 of x2 is equal to x1 square plus say twice x1 x2 minus x2 square, then it is multidimensional or multivariable function. More specifically, it is called bivariable function. Okay, bivariable function. And in such case, to two variable. So, I can, if I put this function something like that, I can put this one is say for f(x), x1, x2, and this one is, if I put this x1 direction and this one is x2 direction. So, it in such case it is called multivariable functions and multivariable optimization techniques. So, in this example we will see, we will take this way. If I want to optimize these things, what I have to do? It is very easy. First, I need to make the slope of the function is 0. What, of course, this techniques we have seen in our calculus classes in higher secondary. So, if the optimal point is x occurs where the slope is 0, and the first derivative we put this one 0, and whether it is maximum or minimum we can put this one. If double derivative of the function is greater than 0, that means it is minimum. If double derivative of the function is less than 0, then it is maximum. Graphically we can observe this also. Say I have a function something like that, say for I have a function something like that. Something like that, okay. Say I have a function something like that. I have a function something like that, okay. Now, slope of the function is this. This denotes that here this one, this f1x, that means this one f1x, that means d fx by dx is equal to 0, that means it is horizontal. So, this one is here. I can tell that when the tangent at that point where the tangent is horizontal to x axis, then it is the point of minimum point of the functions. And what is this? This one, if this one is greater than 0, that means if I differentiate the function, if this one is greater than 0, then so this one I am coming and this one greater than 0, then it is basically we have reached a minimum point, okay. And if the function we have reached the function, if the function is double derivative of the function is say this one, okay, then this point. So, this one, that means if double derivative of the function, if it is less than 0, that means in first quadrant, then it is we have reached the maximum point. This is the rule for single variable functions. The for multivariable or bivariable functions, this technique is slightly differs because of the fact if there is a more than one variable, we have to take partial derivative of the functions, then we calculate the gradient matrix, then Hessian matrix, then we can conclude that this is the maximum value or minimum value of the function. This is the value of the particular parameters at which the function reaches maximum value or minimum value. Okay. So, let us come to the what are the methods reaching maximum value or minimum value. We require derivative information. It is simple applicable for differential function. If the function is discontinuous in nature, we cannot use this. So, we can reach the optimization methods for reaching the derivative method, as I have just discussed. We can reach the optimized value to using Newton-Raphson's methods, and we can some another methods are there for quadratic approximation. We can reach the maximum value of the functions. So, in the examples I have given you, that one, the say if the function is this one, x square plus 3x plus 2. So, if this is 1, so we see this one, and we put this value to 0, we reach this one. That means, I can tell that function reaches minimum value at minus 1.5, and at the double derivative of the function is 2. So, it is basically it is minimum value at x.5 minus x.5. That means, function is something like that, I can easily tell from this function is something like that, reaches minimum value. That means, this one function is something like that, x value x0, that means this one something like that, this value is basically 2. So, in this example what we have discussed? We have discussed the different techniques of optimization, different classification of optimization techniques, and we have the primary methods of optimization techniques for single variable functions, and then single variable functions. The basic steps are basically you take first derivative of the function and put this derivative to 0, get the value of parameters or x, and this is the parameters or value where function reaches to its maximum value or minimum value. To test the maximum value or minimum value, we take the double derivative of the functions. If the double derivative of the function is greater than 0, then it is minimum, and if the double derivative of the function is less than 0, then this point is a maximum value. We will discuss in the next few videos for optimization technique for multivariable functions also. Till then, goodbye.